Okay guys, so this is transition elements or transition metals, and basically what we're going to start off is doing a little bit of a recap on the electronic configuration of, well, anything really, but specifically transition metals. So first of all, let's remember, we always fill up from our lowest energy first, and if I was to do a scaling of the lowest energy shells and subshells, it would look like this. My 1s subshell is the lowest energy, so that gets filled up first, then 2s, then 3s, then 3p, but 4s is lower in energy than 3d. So 4s will be filled up with electrons before the 3d subshell. However, once 4s is filled up, it becomes higher in energy than 3d. And when we remove electrons, we always remove them from the highest energy. So 4s is like a commando, it's first in, first out. It gets filled with electrons first, but will also lose its electrons first. So I'm just going to draw a few electronic configurations of iron, cobalt, zinc and scandium. And iron, I can find my sheet, will look like this. I'll do my electrons pointing up and down because they need opposite spins. We'll then have 6 electrons in my D subshell. If I had iron 2+, I would remove these 2 electrons first, removing them from the 4s before the 3d. So cobalt would have this configuration. It's got 1 more electron than iron. And again, if I had cobalt 2+, I would remove those 2 electrons there. Okay. Now, a transition element, or a transition metal, is an element which has an ion with an incomplete D subshell. So you can see iron and cobalt, they both have ions, 2+, with an incomplete D subshell. So these are transition elements. However, some elements are not transition elements. The only ion which is the only stable ion which zinc forms is zinc 2+. Now, if I was to draw zinc, zinc would look like this. So zinc 2+, I remove the 2 4s electrons first, and you see the only ion of zinc does not have an incomplete D subshell. That's full. So zinc is not actually a transition metal. And it's very similar for scandium. Scandium has got 3 electrons, but the only stable ion which scandium forms is 3+, where I would remove all of these electrons, the 4s first. So you can see this does not have an incomplete D subshell, it has an empty D subshell. So scandium and zinc are not transition metals or elements because they do not have incomplete D subshells. What differences will this make? Well, not only will these not have a very wide range in oxidation state, these are basically the only oxidation states they can have, but they will not be, well, tend to not be as coloured. Transition metals are very, very coloured. They're really pretty if you put them in solution. They also make really, really good catalysts. So 2 differences you could say between a transition metal and a non-transition metal is that transition metals are coloured and they're really good catalysts. Okay. In terms of electronic configuration, there's also 2 slightly weirder ones which you need to know about, and that is chromium and copper. Okay, now chromium has, you would think, and you can check your periodic table to figure out how many electrons it has, you would think chromium would have an electronic configuration like this. So it would be 4s2, 3d4. However, elements are more stable if they have an equal number of electrons in each of their d subshells. In each of their d orbitals. So you can see here, I've got 1 in this d orbital, 1 here, 1 here, 1 here, but no electrons there. And not having an equal amount in each makes this chromium unstable. So atoms like to be stable, that's what they want to do. In order to make itself more stable, what it does is it shunts one of these 4 s electrons into this orbital here. So if I was to draw the electronic configuration for chromium, it would be 4s1, 3d5. So we can have an equal number. And very similar reason is why copper also has a 4s1 configuration. You would imagine copper looks like this. So you'd think it was 4s2 3d9. However, again, because this would give it 2, 2, 2, 2, 1, that has an uneven number. So what it does is it shunts one of its 4s electrons into its 3d subshell. So the electronic configuration of copper would be 4s1, 3d10. Okay, and again, that's just to make it a little bit more stable. Okay. Your transition elements are very, very good catalysts and coloured because they can have variable oxidation states. So manganate, for example, can be anything from +1 to +7. So there's a lot of differences there. And sometimes it's quite difficult to remember which of those oxidation states they would prefer to have because there's so many to choose from. So although they can exist in more than one, they always have a preferred one. And there's a little word mnemonic which you can use to help you remember this. So if I write down my elements as I go across the first row of my transition metals, now obviously scandium is not actually a transition metal, but we'll include it anyway. There's scandium, titanium, magnesium, chromium, manganate, iron, cobalt, nickel, copper, zinc. Okay, now the little word mnemonic you need to remember is all good boys get to see it is on TV. All good boys get to see it is on TV. If we look at the number of letters in each of these words, that tells you the preferred oxidation state of that element. So scandium has a preferred oxidation state of +3, titanium +4, vanadium +4, chromium +3, manganese +2, and so on and so on. Okay, so all good boys get to see it is on TV. Okay, thank you very much.